Hello everyone. Let us today continue from the previous lecture where we left with. So if you remember, I have asked you to find a characterization when a point belongs in A interior, right? So let me answer that first. So whatever you want to call it, theorem or result. So theorem, it's a like sort of characterization. So let X tau be a topological space. And A is sitting inside X. So A is some subset. Then X belongs to A interior if and only if there exists an open set. So what is open set? The members of topology, of course, right? This we have done a lot. So now we are comfortable with this thing. So there exists U in tau such that X belongs to U, which is sitting inside A, wholly lies in A. So that is what I want you to find, like to observe this property. And as you might see, if you have done metric spaces and some kind of topology on real line in your undergraduate courses, you know that that is how we define, right? Something called interior points, if I am not mistaken, using the concept of balls, of course. But yeah, it is analogous to that. So let us prove this fact. So let's go in this direction. Let X belongs to A interior. Okay, what it means, guys? What is A interior? Note that A interior is the largest open set contained in where A, of course, right? So, in other words, what is A interior? This is basically this we have observed. If you remember, what is A interior? Union, right? A interior is union of all U such that U contained in X is of course open and U is sitting inside A. So basically this thing, right? Now guys, X is where? X is in A interior. It means X is in this thing, this union, right? So let me say RHS, okay? Right hand side, I mean this union. What it means? If something is in union, it means that it is in at least one of them, right? So this implies there exists an open set U such that, of course, it should be inside A, right? That's what the definition is. So such that is in U and which is precisely contained in A. So you see, this is a, very simple observation. And converse, I leave up to you guys to verify. Okay. So please prove it. Now, let us proceed. So this is about A interior. So if you remember, last time we have also done something about A closure, right? A point is an A closure if every open set containing that point intersect the set, right? So let me just, define one or two more things. Let's have definition. This I promised you last time, but I think I have forgot to define. So boundary of a set. Of course, in topological space, few people also call it topological boundary because there are also other convention of boundary. One you will find when you will be studying theory of partial differential equations. So let me not go into that because that's not our goal. So let me define boundary of a set. So again, let X star be a topological space and A is inside X. Okay, then boundary of A is denoted by this symbol del of A. It's not partial derivative, please note that. So del of A, of course, you cannot, take partial derivative of a set. I mean, it doesn't make sense. So boundary of A such that, okay, and defined as how it is defined as given by or defined as follows. So boundary of A is nothing but A closure intersection. You take the complement of A and its closure. Okay, guys, let me tell you, this actually, captures the idea of your boundary. What do you, if I ask you a simple question, what is the boundary of open interval 1, 2 in real numbers? You will say 1 and 2. Let's see why. So that is the idea, right? Which, like I told you, the mostly things are, motivated from nature in topology. So we should have respect for that idea. And then, of course, we proceed and see various other things. So let me have an example. So let us consider real line R. You know what is the topology? I'm not stating again. Now, real line R. So let us take A to be open interval 0 to 1. Guys, what is A closure? I hope you have solved a few problems on finding closure of a set. I have discussed few. So this is this. And by the way, what is complement? This is minus infinity to 0 union 1 to infinity, right? So what is the closure? The closure is the set itself here. Basically, the set is closed. Now, so I think this is very clear. The boundary of A would be what, guys? 0, comma 1. So you see, so this definition captures, the idea of the usual boundary. But is it limited to that? Of course, no. Like the word open and close we discussed, right? You a door, like, okay, no, that's not a right example. So yeah, like that. So it is like it's a pathological thing we have. Okay, this definition is motivated from the usual thing, but what about, like, is it limited to this idea? So the answer is no. So let me have one more example, guys. Example two. I hope I have discussed these kind of examples. So let us consider, okay, X along with tau COF. What is tau COF? Cofinite topology on X. And or where X is infinite. Okay. Now let me let us check what would be, the boundary of few of the sets. So let us consider. So let capital A inside X be infinite. Now my question is, guys, what is A closure? Can you tell me? So what would be the A closure? It is the smallest closed set which contains A, or a point will be in A closure if you take any open set around that. If you take any open set around that, it should intersect A closure, right? What are the open sets in cofinite topology? What are the open sets? Open sets are complement of finite set. This is the infinite set. So you see, every open set, so every open set in X tau of will intersect what? A, right? If we have done this already, so I'm not repeating the argument. So what is A closure, guys? X. Okay, very nice. Now let us see what is the complement of A and its closure. So X minus A. So if you see, what is X minus A? It's a finite set, right? X minus A is a finite set. And what is the closure? My question is, what is the closure of it? Can you tell me? Think for a moment. You can stop the video and try it on your own, because if you remember, we have done these kind of things. I'm not doing anything new here, right? So let me proceed with the answer. So this would be precisely X minus A, because it's an infinite set. Its complement would be, okay, no, this is not true actually. This is false. So let me have something else. Sorry, I'm sorry. Let me just take a infinite open set. Sorry, huh? Yeah. Now I think this would be what? Closed. So this is precisely this thing. Now, so it's an infinite open set. Of course, just an open set I'm taking. So what would be the boundary of it, guys? So the boundary of A would be X intersection what? X minus A, right? So what it is, guys? X intersection, the complement of it. So it is nothing but X minus A. Let me just recheck. Okay, so I have a open set. I don't need to write here infinite. It would be automatically infinite. So I have a open set. So it means its complement is closed. So X minus A closure would be X minus A. This is fine. And since its complement is finite, so every open set has to intersect with it, right? Right? So what we have seen here, guys, boundary of A. Boundary of A is what? Its complement. It's like something like this. So you have this whole space, you have A, and everything here is boundary. So like for example, if you take in particular, if you take say what say R along with tau cofinite topology, and if you take your set A to be, let us say R minus 1, 2, 3, 4. So what you have seen here, guys, the boundary of this set, this A is what? 1, 2, 3, 4. That is what you have observed. And one more thing. So this is example 2. Let's have one more example. Example 3. So what if you take something like this? Let us consider R with Euclidean topology. You know what I mean is R with the real line R basically, the usual metric, the usual distance. Okay, now guys, what about this set? Let's say 1, 2, 3. So if you see A closure is what? A. And what is X minus A? So X minus A closure would be what? So if you want to see this, excluding these 3 points, right, it would be the closure of minus infinity to say 1 union. Okay, 1 to, sorry, open interval. Open 1 to 2 union, open 3 to infinity. It's closure. Right, guys? So what it is? Can you tell me? So it's the whole real line. You can check. So what you have observed here, guys? What would be the boundary of A? It would be the set itself, right? So the boundary is the set itself here. So you see, the concept of boundary is definitely motivated from the human intuition, but it is, something different. Because if you ask a layman what is the boundary of this set, he will say, these are just points. It should be there should be no boundary, right? But what is the case here, guys? Its boundary is precisely the whole set, this whole set, 1, 2, 3. I hope this is clear, right? So this example I wanted to give you. Okay, good. So this is about the boundary of set. That's what I wanted to you guys to know. And now I think for now these kind of concepts I can stop with just one more definition. So definition: limit point. We also call it cluster point. Also call it accumulation point. So let X tau be a topological space. And A is inside X. Okay, so number one, we say X in X. We say X in X is a limit point of A if So this is the definition. Limit point is a point in closure, but with some, with some minute difference. So if every open set U such that X belongs to U. So you have to take all open set such that X belongs to U. So what you should have, that's what I'm gonna tell you. We must have U intersection, not just A guys, A other than the point X. It is possible that A also contain this point X. It should be non-empty. So that is what these points we call limit points. So you can clearly say that if you have a limit point, it is definitely inside closure, right? Because a point X belongs to a closure if and only if, right? Every open set containing that point should intersect A. So every limit point is a point in closure, but every point in closure need not be a limit point. So let me write this remark, every limit point of set A belongs to a closure, but converse is not true. Why? Basically, there are points which are in closure, okay? There are points which are in closure, but not in the set. That I will leave as homework. You might have done many examples in real numbers. I want you guys to try, in some different kind of spaces. So let me end this session right now because like there are many more things to tell, but I will be telling those things if necessary in future. But for now, about these derived concepts, two things are very important and we have done closure and interior. That's what my main goal was. Now, in coming lectures, we will be learning about something called basis. The concept of basis we will see in topological spaces. Thank you for your attention. Let us see you guys in upcoming session.